Hello everyone, welcome to Engineered Learnings. Engineered Learnings has been created as an effort to help and reach out to all the engineering students, aspirants and professionals out there with the basic understanding and the crux of the topics important for placements, vivas, semesters, competitive examinations and all types of interviews. So let's go to today's topic. Hello everyone, welcome to today's video. So before going to today's video, thank you very much. We have reached 1k subscribers this week. Finally 1k after a lot of struggle, after a lot of chaos over the efforts. But the efforts has been worth it because people have been associated with us and we have really appreciated the efforts. Now there are going to be some people that are always going to try to pull you down, but nevertheless with the help of our audience we have crossed 1k subscribers, and for that, thanks to each and every one of you who has subscribed to our channel or who has viewed our content or has supported our content. Thank you very much. So today, since we have crossed 1k subscribers, we are going to return to the basics from where we started from, the basics of it all. So today's topic is Pvt diagram, that is pressure, specific volume and temperature diagram. A very important diagram. Now this diagram, I always have it printed in my mind, and whenever I face a trouble or a problem related to pressure, temperature or pressure volume temperature mixed problem, I always go for this diagram. I visualize this diagram and I solve the problem. Trust me, most of the equipments in the industry or most of the processes in the industry are based on this principle, that if you lower the pressure, how the boiling point is going to be affected, or how the saturation temperature is going to be affected. If you push up the pressure, whether that's going to be a liquid state, whether that's going to be a vapor state, all will be clear from this diagram. What is the state of matter at a particular temperature and pressure? This is the Pvt diagram. Very important diagram, very important diagram for industrial practices or for any of the industrial processes. Now I've written the list of a few instruments or a few equipments that actually follow this principle of Pvt diagram. If you straight away go for these equipments, you will relate to this graph and you can jot down that at which pressure what state of matter will be existing, or what states of matter are coexisting in that particular equipment at a particular temperature and pressure. So flash evaporator, crystallizer, vaporizer, boiler, all of these principles are basically associated with Pvt diagram. So let us understand what is this Pvt diagram. So going to the Pvt diagram, we have to describe that this is a 2D graph. So basically you can have a 3D graph if you are drawing for the three-phase diagram to jot down the triple point and all. But I am considering the 2D diagram because it's easier to visualize and understand. So basically this is my pressure axis, this is my pressure axis. So this is pressure and this is my specific volume axis. So it is basically nothing but volume, total volume by total mass. So it is the specific volume, that is the amount of meter cube occupied per gram of the particular substance that is existing there. So it's basically nothing but 1 by density, 1 by rho. So if you write that 1 by density, it will be similar to that. This density, I have a little clumsy expression of pressure and density almost getting similar, but this is rho. 1 by density is specific volume. So definitely specific volume, if the mass is fixed, as the volume increases, volume of the body increases, specific volume will increase. So specific volume increases in this direction and pressure increases in this direction, and this is the graph that is existing. So a kind of a diagram like this is existing in the PV plane, PV diagram. So to visualize it, this is the liquid state. Anything that, just visualize this diagram, just remember this diagram, anything that is in this side of this diagram is a liquid state. This is the liquid state. This is the combined phase state, that is liquid plus vapor, and this is my superheated vapor portion. So this is saturated liquid, this is subcooled liquid, subcooled liquid state, this is superheated vapor state, superheated vapor, this is my mixed phase, that is saturated, that is vapor plus liquid, As I've already written, L plus V, this is liquid, subcooled liquid, this is superheated vapor. As we give heat, vapor is converted. We will discuss that, how it is happening. These are the points of saturation. Now, what is this point? This is saturated liquid at a particular pressure. Saturated liquid. That is, it is entirely liquid, and if you give a little bit of heat to it, a little bit of heat you add to it, it will straight away change into vapor. So it will start forming vapor. So there will be a liquid vapor equilibrium that will be coexisting. And at this point, at a particular pressure, this is my saturated vapor. So we understand that this is my saturated liquid, this is my saturated vapor. Now we will have to understand one thing, that during a phase change, remember, the pressure doesn't change, the temperature doesn't change. Until and unless we externally try to change the pressure. If we keep the pressure constant, the temperature won't change. Whatever heat is incoming is not responsible for increasing the temperature, but the heat is absorbed as m lambda. That is, the heat is absorbed as latent heat of vaporization, and the liquid will start transforming into vapor. That is, the boiling will take place, or evaporation will take place by taking the heat from the source. And the temperature in the process will not increase until and unless we change the pressure. So for a particular transformation from liquid to vapor state, the pressure and the temperature remains constant. What changes is the volume. That is, liquid this much volume will transform into vapor this much volume. So firstly, phase change, if at a particular pressure, supposedly P1, the phase change is occurring, so only with no change in pressure, only the specific volumes of volume will change, because the volume increases in the process. So this is V1, this is V2. So volume of vapor is definitely going to be much greater than V1. So liquid volume, the vapor volume will be much higher than liquid volume, as we can clearly get from the picture. Depending on the mass, obviously, the mass also plays an important factor, but definitely the vapor volume will be higher than the liquid volume. Now, what about the temperature? How do you define the temperature in a Pvt diagram? Very important. I have drawn this curve. If you see, what does this curve, what does this line signify? This line, what does this signify? This is the temperature isotherm line. Very important, temperature isotherm line. That is, if we go by this line in the Pvt diagram, this is an isotherm. That is, its temperature is constant. This line, over the entire line, it is T, 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 and T. Now what is happening during the phase change? During the phase change, if I draw this temperature isotherm, so this is my T1 supposedly, corresponding to P1, my saturation temperature is T1. So what is happening if I draw this diagram like a little fresh, I'm loving this, a little fresh diagram, that this is my pressure, this is my specific volume, and this is probably my graph supposedly, and this is the phase change that is occurring. Throughout the phase change, at a particular pressure, the temperature will remain constant, only the volume will increase. So V1, V2, but P1 is constant, T1 is constant. Now, how do you define a particular state point or a matter point? Now, you're given a temperature, supposedly, you're given a pressure. The pressure is P1 and the temperature is T2, supposedly. Now, T2, remember, is supposedly less than T1. Is less than T1, let's suppose. So the isotherm is going to be something like this, because it's decreasing downwards. Now, as we come down, the temperature decreases. Temperature decreases in the graph as we come down. The temperature isotherms decreases. So T2 is less than T1, supposedly. So what is my state point? My state point is the cutting of two particular points, that is particular temperature pressure. So if you are given P1 and T2, this is the point. So this is my state. This is my state. This is my state point. And what is it? It is liquid. Now supposedly T2 is greater than T1. Or supposedly I take a temperature T3. P1, T3. Keeping the pressure constant, I am changing the temperature. Keeping the pressure constant, I am changing the temperature. Supposedly it is T3 and T3 is greater than T1 supposedly. So it will be something like this. This is my isotherm. And you see, if I drag this line, this is my state point. The cutting point of P1 and T1. P1 and T3. This is my T3 supposedly. This is my T1. The middle one is my T1. The upper one is my T3 because T3 is greater than T1. So the cutting point of T3 and P1, P1, T3, cutting point is superheated vapor region. So you see, P1, T2 cutting point was subcooled liquid. Subcooled liquid in this portion. Whereas my T3, P1 is superheated vapor. And what about my T1, T1? T1 is this, all of these points, it's a mixed state. So it is saturated. Saturated, liquid plus vapor state, anything can be the case. Starting from here to here. It can be this point, this point, this point, this point, this point. So to recognize the exact point, you need the V value as well. Remember, when there is a phase change or a mixed phase, you need 3 data points to actually establish it. To actually understand the concept of it all, like how do you get to know the state point, you need three data points. That is V1 you need P1 and you need T1 as well. So to know the exact state point. If I give you P1, T1, it can be anywhere along the line. Anywhere along the line. So it is a phase change reaction. Now you are getting the point. Now understand this, that at a particular pressure, remember this thing. What happens? At a particular pressure, supposedly 1 atmospheric pressure, water is vapor at 120 degrees Celsius. Supposedly T3 is 120 degrees Celsius. 120 degrees Celsius. P1 supposedly is 1 atmospheric pressure. T1 is 100 degrees Celsius. And T2 supposedly is 80 degrees Celsius. So at 80 degrees Celsius, at 1 atmospheric pressure, the state point is liquid. At 1 atmospheric pressure, at 120 degrees Celsius, the state point is superheated vapor. And at 1 atmospheric pressure, at 100 degrees Celsius, it is saturated liquid plus vapor combination. It can be anything in between. That is, it is a coexisting phase. That is, boiling has started. So you understand that depending on the pressure kept constant. Pressure kept constant. If we change the temperature, the state matter will change. Similarly, temperature kept constant. If we change the pressure, the state matter will change too. So if I draw this graph once again, so what happens at a particular pressure, supposedly, this is my pressure isotherm. At a particular pressure, P1, this is my saturation point, saturated liquid point, this is my saturated vapor point. And if I have to draw the isotherm, that saturation temperature means at P1, I keep on increasing the temperature. I keep on increasing the temperature till it starts boiling. So my boiling point on a boiling temperature is going to be that temperature at which the vapor formation will start. So what happens is, supposedly at T1, it is a subcooled liquid, firstly. I increase the temperature a little bit, so the isotherm goes like this. At T2, it is still a subcooled liquid, but it's tending towards vapor state. It's tending towards vapor state. I keep on increasing the temperature. Supposedly 1 atmospheric pressure. This is 50 degrees Celsius, T1. T2 is 70 degrees Celsius. I keep on increasing and I reach 100 degrees Celsius and the vapor formation starts. So this 100 degrees Celsius T3 is my Tsat, that is saturation temperature or boiling point TB at that particular pressure. So Tsat. So Psat is P1, that is saturation pressure at which the saturation starts taking place, there is a liquid is completely saturated. Now it will start forming vapor, and then it will reach a saturated vapor state and further superheated vapor state. So what happens, and this is the coexisting phase. So for P1 pressure, Tsat is my boiling point, that is saturation temperature. Anything below Tsat, any temperature that is less than Tsat at that particular P1 will result in a liquid. Anything greater than Tsat will result in a vapor state. As you can clearly understand, if we go beyond T1, this is my state point. So this is a vapor state point. So clearly we get the state points depending on the pressure and the temperature of it all. Temperature and the pressure are the driving factors. So if at a particular pressure, if I boil the water, if I increase the temperature of the water, first Tsat will touch, it will start forming vapors. Further increase, as it will complete the vapor formation, further increase of temperature will result, because if we keep on giving heat, that is Q, if we increase, keep on giving heat in the system, the temperature will first rise, then it will reach the Tsat, then the phase transformation will occur, no temperature rise will take place. So first temperature will go from T1 to T2 to Tsat, then it will remain constant at Tsat, liquid to vapor transformation will occur, then from Tsat it will go to T3, supposedly not T3 but T4, supposedly T4. Being T1 is less than T2 is less than Tsat is less than T4. So you can clearly understand that as we go on, first the liquid tends to formation of vapor, then it converts into vapor where there is no temperature rise, and further increase will result in a greater isotherm. Now, what about this point? This is the point where the temperature isotherm is critical temperatures, Tc. Very importantly so, because beyond this point, no further phase change occurs. So at a particular pressure, supposedly P1, if we change the temperature, or if we like decrease the for a particular let's consider for a particular pressure, if we keep on decreasing the isotherm, that is Tc, the state will not change. Or if we keep on increasing the Tc or decreasing the temperature, the state point will always be gas, because beyond this point, beyond the temperature isotherm of Tc, beyond the temperature isotherm of Tc, no further, this is completely gas. And there is a difference between gas and pressure, gas and vapor. Vapor can be transformed back into liquid, but gas cannot be, because it has reached beyond. This is Pc, Tc, this is my state point, Pc, Tc, single state point, critical point. Beyond Pc, Tc, the entire state of matter is gas. So if we like change the temperature or pressure beyond Pc, Tc, try to adjust that, no phase transfer will take place. This is my critical point. This is my critical point. This is the definition of critical point. Beyond critical pressure, beyond critical temperature, if you try to decrease that pressure, increase the pressure, decrease the temperature, increase the temperature, the gas will remain as gas. It is not vapor, it will not transform back into liquid. But here if you change the pressure temperature, as we have already seen, the liquid to vapor transformation does occur. Now similarly, if we keep the temperature isotherm fixed, that is temperature constant for a particular process, very important, people get confused in this, that if we keep the, supposedly my temperature isotherm is fixed, T1, fixed temperature isotherm, I keep on changing the pressure, what will happen? Now what is happening is, supposedly first pressure point is this, P1. What is my state point? It is liquid. It is subcooled liquid. I further decrease the pressure. This is my second. Still liquid but tending towards vapor. Understand this. This is P2. Supposedly, this is my P3. So at P3 pressure, at that particular lower pressure, the saturation will start taking place and the vapor conversion will start taking place. So my P3 will become my Psat for T1. For particular temperature T1, the saturation pressure is P3, at which the phase transformation starts taking place. Now further decrease of pressure will result in superheated vapor state. So as we decrease the pressure at a constant temperature, as we keep on decreasing the pressure, the tendency of liquid to vapor formation increases. So what happens is, at a particular pressure, at a particular lower pressure, as you lower the pressure, easy evaporation takes place. What happens is, supposedly there is a liquid bath. If we try to understand this practically rather than going by graphically or theoretically, there is a liquid bath and we decrease the pressure in this section. So what happens is, this creates a vacuum and hence there is a lower concentration of water here. So in this process, the low pressure zone will be taken by the water. So the water will evaporate in turn to take its place, like it happened in sea breeze. We see land breeze and sea breeze. We have studied earlier in our junior classes. What happens? The liquid will try to evaporate and take the place of the low pressure zone. So as we decrease the pressure to attain equilibrium, the evaporation will start taking place. So liquid will try to convert into vapor as we decrease the pressure at a constant temperature. So by this graph, we can conclude that if we draw the conclusive points, this can be concluded that as we decrease the pressure, the vapor formation tendency increases. So we can straight away write that at a particular temperature T constant, if P decreases, vapor formation tendency decreases. Vapor formation tendency increases. So liquid will try to convert into vapor. This is the concept. This is the concept of flash evaporation, crystallizer, vaporizer. Now many people do confuse. What happens is, in a flash evaporator, it is flashed. The system is flashed. That is the sudden decrease, sudden throttling, sudden decrease of pressure allows throttling. The process is called throttling. The sudden decrease of pressure allows the formation of vapor easily at that particular temperature. There is also the principle that is followed in AC. We will also discuss that in our next video. That is, we are going to come up with that AC versus cooler. What is the working principle of it all? So what happens is, this is flash evaporation technology, that if you decrease the pressure, sudden decrease of pressure causes the liquid to vaporize easily. As we decrease the pressure, liquid will try to vaporize easily, as we can understand by the Pvt diagram. Now, for P constant process, that is isobaric process, this is isothermal process. Isothermal, that is the temperature remaining constant. Isobaric process, that is pressure constant. If pressure is constant and temperature is increased, the vapor formation tendency increases. The vapor formation tendency increases as the pressure is constant. Suppose the pressure is 1 atmospheric pressure. 1 atmospheric pressure, the fellow will start boiling at 100 degrees Celsius and will turn into superheated vapor at 120. So the fellow that was a liquid at 80-90 degrees Celsius will boil at 100 and will turn into superheated vapor at 120 degrees Celsius. And as the temperature is constant, a fellow that used to boil at 100 degrees Celsius will now start boiling at a lower temperature if the pressure is decreased. What does this mean? This means that supposedly this is my graph. So for this pressure, for a higher pressure, we need a higher isotherm to cause the boiling of liquid. As the pressure is decreased, we need a lower boiling isotherm to convert it into liquid. Now, if the P2 is less, then Tsat is also less. This is the concept of it all. That if the pressure is less, the boiling point also decreases. Thus, easy boiling or easy vaporization takes place at lower pressure. So, if the temperature is increased, vapor formation tendency increases. If the pressure is decreased, vapor formation tendency increases. So, this is the concept of it all. During phase transfer, phase change, no temperature change or no pressure change occurs. Only specific volume change occurs, and beyond critical point, no phase transfer or no phase change at all occurs beyond this point. This is completely gas This is no liquid, no vapor. This is liquid plus vapor. This is vapor, but this is completely gas, no phase transfer occurs. I think this is the basics of it all. And if you get it clear, you will understand what happens when we decrease the pressure, what happens when we increase the pressure, what happens in a flash evaporator, in a crystallizer, the water evaporates at a low pressure, what happens in a vaporizer, what happens when we try to boil a liquid at a lower atmospheric pressure. Obviously, at a lower atmospheric pressure, like 0.5 atmosphere, the boiling will be easy because the boiling point has decreased. So at a lower pressure, the vaporization will start easily. So at a lower pressure, you will have to increase the pressure. If you go in the hilly regions, a pressure cooker is used to cook the rice because the pressure at hilly regions decreases. So you need to cook it at high pressure so that the water will take a greater time to boil off. If it is 1 atmospheric pressure, water will boil at 100 degrees Celsius. But if it is 0.5 atmospheric pressure, the water will start boiling at 80 degrees Celsius, 70 degrees Celsius. So the pressure cooker is deliberately used so that the pressure can be made 1 to 1.2 atmospheric pressure so that the rice gets time to boil. That is, the water doesn't get vaporized easily. It takes time to boil. So this is the concept. You can vary the pressure to decrease or increase the boiling point, to ease the vaporization or to decrease the vaporization rate. That is, I think, will conclude the Pvt diagram lecture for today. If you liked it, like it, share it with your friends, subscribe to our channel. Thank you very much.